Hi, welcome to Module 6 of Lecture 6. In the previous module, we talked about the first derivative test and listed the first order condition, which helps us determine when we had a stationary point. Now, a stationary point is a candidate for an extremum because it can be either a minimum, a maximum, or an inflection point. To figure out which one it is, we employ what's called the second derivative test. The second derivative test entails computing the second derivative. So you compute the second derivative, right? So f prime prime, evaluated at the stationary point here, x star. Remember, x star was the stationary point. It's the point at which the first derivative is 0. And note, in this latter equation, we're implicitly defining the stationary point x star. An implicit definition of some variable x star is a definition in which you define what x star is by virtue of its ability to, say, solve some other equation without actually explicitly solving x star equals blank. Here it's implicitly defined as the variable, or in this case the function, that makes f prime equal to 0. Okay. So you evaluate the second derivative at the stationary point x star, at each stationary point, and you check to see what the sign is. If the sign is positive, you have a local minimum. If it's negative, you have a local maximum. The reason, again, is for a minimum, you have a locally convex function like this. As we saw, the stationary point would be the minimum. If it's greater than 0, if it's less than 0, you have a concave function like this, and the stationary point would be a maximum. Now, if it's equal to 0, you have an issue. You haven't shown us a maximum, you haven't shown us a minimum. The second derivative test is inconclusive. I should say that all these three conditions together form what's called the second order conditions. We're trying to understand the second order derivative and the conditions under which it determines if you have a maximum or a minimum, or maybe one or the other or neither. So when it equals 0, you have something of an issue. You haven't determined if it's a maximum or a minimum yet. So what do? Now, I have a little longer description in the book, but for our purposes, the easiest thing to do is to think about higher derivatives. So, and let's talk, we can think back again towards x cubed, in which the stationary point here was neither a maximum nor a minimum, it was an inflection point. So what we're trying to understand is whether or not the curvature of the function changes sign around the stationary point, in which case you have an inflection point, whether it doesn't change sign. For an example of that, consider x to the fourth. This is x to the fourth. There's a clear minimum down here, despite the fact that x to the fourth has a third derivative of 0 at 0. Right? You can check that. X to the fourth, so f prime equals 4x to the third, f double prime equals 12x squared, f triple prime equals 24x, and f fourth derivative equals 24. Which is positive, and for every other one, though, is 0 at x equals 0, which is the stationary point. Why is it the stationary point? Just to make sure, because it's the point at which f prime equals 0. That's x equals 0. So, these are very different functions, obviously. In the case of x cubed, this is a stationary point over here. I'm going to put this in red. This is a stationary point. In the terms of x to the fourth, it's a minimum. How can you tell a difference? In both cases, the second derivative gives you 0 at that point. Well, it turns out it's pretty easy. You keep computing derivatives until you hit something that's not 0, right? In the case of x to the third, the first non-zero derivative is the third derivative. In the case of x to the fourth, the first non-zero derivative is the fourth derivative. What do you do with that? Well, at the point at which you hit a non-zero derivative is an odd derivative, so the third derivative, the fifth derivative, the seventh derivative. If you hit an odd derivative as the first derivative that's non-zero, then you have an inflection point, just like you had for x cubed. So for instance, if you were to graph x to the fifth, you'd also find an inflection point at 0. The third derivative would be 0, the fourth derivative would be 0, the fifth derivative would not be 0. So anytime an odd derivative is the first derivative not to be 0 at the stationary point, which mind you can be different from 0, just a stationary point. If the first derivative not to be 0 at some stationary point is an odd derivative, you have an inflection point, and it is neither a minimum nor a maximum. If the first derivative not to be 0 at a stationary point is an even derivative, such as the fourth derivative for x to the fourth, then you can treat it just like you treated the second derivative. Namely, if it's positive, so if the fourth derivative is positive, you have a minimum. If the fourth derivative is negative, you have a maximum. Same thing for the sixth. If the sixth derivative is the first one that's non-zero, then if it's positive, you have a minimum, and if it's negative, you have a maximum. And so on for any even derivative that happens to be the first derivative that's non-zero at the stationary point. That's it. And again, all that complication arises not from the most basic second derivative test, which is these two parts of the condition, which are just if the second derivative is positive, it's locally convex, therefore it's a minimum. If the second derivative is negative, it's locally concave, and therefore the second derivative is a maximum. That's the core concept to get. If you get that, you're set. Everything else is fairly special cases that don't occur that much, but you should know that if the second derivative is 0 at the stationary point, your test is inconclusive. You test more derivatives until you find the first one that's actually not 0. If that first one is an odd derivative, then it's an inflection point and neither a minimum nor a maximum. If that first derivative that's non-zero is an even derivative, then you treat it the same way you did for the second derivative, namely if that first even derivative is positive, it's a minimum, and if it's negative, it's a maximum. And that's it. In the next module, we're going to go through and we're going to put this all together, the two tests together, refer to a nice discrete set of rules that's also in the book, and give a brief example of how to do this. Thank you very much.